Welcome to this demo of the UFS Land Data Assimilation System, otherwise known as Land DA. As a bit of introduction, the Land DA system is based on the NOAA MP Land Surface Model, and it performs JEDI-based snow data assimilation using the local Ensemble transform Kalman filter optimal interpolation algorithm. In this video, I'm going to show users how to run this system on the MSU Orion machine, but Land DA is also supported on NOAA's Hera machine, and containers are available so that users can run a release version on other systems. Before I begin, I'd like to point users to resources that may be helpful when attempting to replicate the steps provided in this demo. Generally, the Land DA User's Guide is the best place to start. It has the most updated information on the workflow. That said, development is ongoing, and sometimes documentation there is slightly behind where the development is. This is why the repository's GitHub Discussions feature is also incredibly helpful. You can ask your questions there if you run into issues, and we'll get you connected to someone who can provide an answer, usually within about 48 hours. For those who are curious about the details of the science involved in the NOAA MP model, the technical documentation is also a helpful resource. And for the data assimilation, the JEDI documentation is indispensable. Beyond that, we have resources linked from the Land DA page on the EPIC website, and we also have a lot of the resources linked on the GitHub wiki. Finally, if you're looking for data, you can access data in the Land DA data bucket. If you go to Browse Bucket, there is Develop Branch Data with a date stamp, and then there's current release data for all of our past releases. The version 1.2.0 release is the most recent, and we have the Land DA input data in a tar file, and we also have a release container there for easy download. Before I begin to run through the code, I want to quickly introduce the experiment. I'll be running through the default case provided in the Land DA workflow configuration file. This case runs NOAA MP as the land component in the UFS Weather Model. It uses GSWP3 forcing data to run through a 2-cycle experiment for January 3rd and 4th, 2000. The software stack supporting Land DA is currently SpackStack version 1.6.0, and it's used alongside JEDI Skylab version 7 for data assimilation. I'm using the latest develop branch code. The commit at the time of recording for that is 09F445E. Okay, so here I'm already logged into Orion, and if you're trying to run Land DA, you'll need to log into a system where you have access. From here, I'm going to navigate to my project space and create a directory where I'll do all my Land DA work. So I'll cd to /work/NOAA/epic/gpetro, and then if I run pwd, you can see that that's my present working directory. If you're trying to replicate this experiment, you can do your work in whatever directory makes sense to you, as long as you have write permissions there. So from here, I'll create a Land DA directory using the makedir command, and then I'll navigate into it using cd. And then again, using the pwd command, you can see that I'm now in my Land DA directory. It can be really helpful to save this directory in an environment variable so that you can return to it more easily. This is an optional step, but it's usually easier than remembering and typing out full path names, especially if you're running multiple experiments and need to switch between directories. So here, I'll use Land DA root as the name, but you can pick anything that makes sense to you. It's important to note that the backticks around pwd are backticks, not apostrophes. The backticks are usually located right below the escape key near the top left of the keyboard. To see whether this worked, you can run the echo command and access the newly saved variable with the $sign. That should print out the Land DA directory path saved in Land DA root. Note that these steps are not required. You can choose to do your work in an already existing directory if you prefer, and you don't need to save the directory as an environment variable if you don't want to. but I find that these steps help me to keep track of my Land DA work better. From here, I need to get the Land DA code. All of our UFS code can be found in publicly available GitHub repositories for anyone to access. I'll use a git clone command to copy the code onto my system. Here I'm cloning the develop branch code because it has all the latest workflow features and updates since our version 1.2.0 release last December. But if you prefer to work with the static release code, you can change the -b develop portion of the command to say -b release /public -version 1.2.0 instead. You'll just need to make sure to follow the instructions in the release version of the user's guide, rather than the develop version. Another thing to note in this command is the recursive option. This option will make sure to get not just the top-level Land DA code, but also any other code used by the system, such as the physics and the JEDI DA increment code. By default, when you clone Land DA, the code will live in a directory called Land DA Workflow. Next, I'll navigate to the SORC directory, which is where all of the source code lives. You can use the ls command to see what's already in the directory. From here, I'll compile or build the Land DA system, as we say, by running the Land DA build script. At this point, you may have to hit enter to make sure that the build continues with the currently loaded modules listed. Once the Land DA system is done building, the console output should end with a message saying that the UFS Model FD code is 100% completed and the UFS Model FD target is 100% built. You can also check in the exec directory, which is up one level, where there will be a number of executables built. And here you can see that we have the apply increment executable, the land model executable, vector to tile and tile to vector converter executables, and the UFS weather model executable. This is exactly what we'd expect from a successful build. Once Land DA is built, the next step is to load the modules required for the workflow. So first I'm going to navigate to the Land DA workflow directory and then load the modules with the module use module load statements. It's important to load the module that's appropriate for the system you're working with. So I'm loading the workflow Orion file, but a user on Hera would load the workflow Hera file. After running the module load statement, you should see a message that says to activate the workflow environment, which uses the modules we just loaded. So I'll just run that command here. If this is successful, you should see Land DA in parentheses in front of the command prompt, which we do see here. This Land DA workflow environment basically just makes all the software you need available so that you can run the workflow somewhat automatically and not have to worry about what you need for this project clashing with what you need for some other project. In fact, every time you want to get back to Land DA work after logging out of the system, you'll need to go to the Land DA workflow directory and run the module use, module load, and conda activate commands again before trying to run the rest of the experiment. You should not need to reclone or rebuild the app in most cases. Okay, the next step is to configure an experiment, and for this I'll need to go to the parm directory. I'm already in the Land DA root Land DA workflow directory, so I can just do cd parm. And if I want to check, got my pwd command. All right, to see what's in the parm directory, I can use ls. And here you see a couple of land analysis YAML files. The Hera and Orion land analysis files contain basic experiment configurations, but the workflow expects a file that is specifically named land_analysis.yaml. So we can just copy the contents of the Orion specific file to land analysis YAML. To open the file, you can just use the vi command or vim or the command for whatever command line editor you prefer. I'll just use vi. Once the file is open, you can see that the machine is Orion and the account is Epic. Any user who's not on Hera or Orion will need to adjust the machine name and use the container-based build instructions. Regardless of the machine you're on, most users will need to adjust the account name to reflect the name of an account where they can charge their computational resources. So I can charge to the Epic account, and in the past I've also charged to HFV3 GFS. Different users will have different accounts available to them. You can just press I for insert to start editing the file. One thing everyone will have to change is the experiment-based directory path, which is right here. This should be set to the absolute path of the Land DA root directory that I saved earlier. So for me, it's /work/NOAA/epic/gpetro/landda. The path is a string literal, so you have to type out the whole path instead of using environment variables. The path also has to point to an already existing location or the workflow won't run. If you ever get into a situation where you're not seeing any workflow progress when you check the status, it's always a great idea to check and see if your experiment-based directory path is correct or if maybe there's a typo in there. As far as other variables to adjust, you can change any of them to fit your system and experiment, but some you'll alter more regularly than others. For example, you might want to choose different forcing data. The default is GSWP3 data, but if you decide to use Error 5 data, you'd have to change this out. And we have the comment right here showing you what you can write instead. You may also be running different cycle dates, at which point you'd have to change the cycle def spec values. Those are up here at the top. Cycle def and spec gives you the current default, which is our case from January 3rd, 2000 with the GSWP3 data. If you wanted to change it to our other default case with the Era 5 data, you just comment out the current spec line and uncomment the Era 5 one. On Hera and Orion, data for our default cases is already available and is linked to the Land DA system when you run the build script. Folks on other systems can download the data from our Land DA data bucket. Once you've made all the changes that you want here, you can press escape to exit insert mode, and then :WQ to write the changes to the file and quit the editor. Now the workflow is almost ready to go. I just need to generate the workflow XML file using the Unified Workflow Rakoto tool, which will translate the land analysis YAML file into a Rakoto XML. This XML file is used by the Rakoto Workflow Manager to keep track of which tasks have been completed and which ones can be started once their dependencies have completed, so that the Workflow Manager can submit the right tasks in the right order. To use this tool, you'll submit a UW Rakoto Realize command with the land analysis YAML file as an input file, and the desired land analysis XML file listed as the output file. After running this command, you can see that there are 0 errors, so we should be set to run the workflow. There are several options to run the workflow. The easiest is simply to automate the workflow run using cron, which will automatically submit the workflow launch script at regular intervals, usually every 2 to 3 minutes. This is great for systems where cron is available because you can just type this. Unfortunately, not all systems have cron, and on Orion, cron only works on Orion login node 1. You can see here that I'm on Orion login node 3. So I'll have to use the Rakoto run command to advance the workflow instead. Whether or not you've automated the workflow with cron, you can use the Rakoto stat command at any time to check the status of the workflow. This command looks just like the Rakoto run command, but it starts with Rakoto stat instead. The Rakoto stat command will print the status of each of the workflow tasks. If I scroll up, you can see the beginning of the database file. You can see that prep obs and pre-analysis are queued with their status here, and then prep obs is queued also for the second cycle of the experiment. Every time you run it, the Rakoto stat command will print the status of each of the workflow tasks. There are 6 workflow tasks per cycle, which are described in the documentation. The first task is the prep obs task, and it sets up the observation data files. The pre-anal task, or pre-analysis task, transfers the snow data from the restart files to the surface data files. The analysis task runs JEDI and adds the increment to the surface data files. The post-analysis task transfers the JEDI result from the surface data files to the restart files. The plot stats task plots the JEDI result. And then lastly, the forecast task runs the forecast model. You can access the documentation at this link below. It'll take you to the specific section of the documentation. When cron isn't automating the workflow for you, you'll have to rerun the Rakoto run command several times, probably every 2 minutes or so before the workflow completes. So for example, I can backtrack and run Rakoto run again. And if I want, I can check the Rakoto stat to see the status. And it shows that those tasks that before were queued have now succeeded. We've got a succeeded message. And then the analysis task for the first cycle is being submitted. Now it's running. The post-analysis and plot stats tasks are submitting. They've succeeded, and now the forecast task is submitting. This is the last task for the first cycle, the January 3rd cycle. Once the first cycle's forecast task has finished running, the second cycle's tasks will be able to run because their dependencies will have been satisfied. And now the forecast task for the first cycle has succeeded, and the pre-analysis task for the second cycle is submitting. Just keep in mind that in real time this will take a little bit longer. For the video, we've cut out all the blocks where we're just waiting for tasks to run. Now we're moving on to the analysis task. For the second cycle, it's submitting. Now the analysis task has succeeded, so the post-analysis task and the plot stats task are submitting for the second cycle. And with those two tasks succeeded, now the forecast task for the second cycle can submit. Once that's finished, we'll be done with the experiment. Here the forecast is still running. And there it succeeded. So with all of the workflow tasks succeeded, we know that the experiment itself has succeeded, and now we can go look at the output. When using the default experiment settings, the workflow directory structure looks something like this. This diagram is already in the documentation in Chapter 2.1 under Run the Experiment, Check Experiment Output. Many of the variables in the diagram are defined in the documentation or will be soon. So here you have our Land DA root directory and the Land DA workflow directory that we've been working in. That's where parm is and where the configuration files are. Parallel to that directory, we have the PTMP directory, and then under that we have the test directory, the com directory, Land DA directory, its version number, and then finally the run directory. All of this can seem a little confusing, but Land DA is striving to become an ENCO compliant repository, so its directory structure largely mirrors the directory structure on ENCO's operational systems. It can be a little counterintuitive for new users, but the documentation aims to clarify any questions users might have. And the good news is that once you've gotten used to this directory structure, you'll probably understand the directory structure for any operational system that you work with in the future. As you may have noticed, the Land DA workflow includes plotting tasks for each cycle. So if you want to go view those images, you can find them in the cycle run directory under plot. For the January 4th, 2000 cycle of this experiment, that would be at this path. We can do an ls to see what's in there. And you see two plotting files. One is a histogram, and the other is a scatter plot. The plots are stored as PNG files, and depending on your system, you may be able to view the plots or download them via a secure copy to your local system to view. That said, instructions for this are highly machine dependent, so I won't go into the details here. Users should reference the data transfer documentation for their system. On my system, I have XQuartz installed, which will allow me to view these images once I load the ImageMagick module. So if I do module load ImageMagick, I can then use the display command to bring up the PNG of the scatter plot or the histogram. And here is the scatter plot over the global map. It shows snow depth observations minus analysis. So where the observations minus analysis number is negative, you'll see blue dots. Where observation minus analysis numbers are positive, you'll see red dots. Should be white or very pale somewhere in the middle. And so this helps us to see where the analysis is over or underestimating the snow depth. One thing to keep in mind, if you try to use ImageMagick XQuartz, you need to be Xlogin enabled. So, for example, I would have to SSH with a -X option into my account, and so on. If you're not Xlogin enabled, it will probably bring up an error message, but you can just close the window, log in again, navigate to your directory, and load the ImageMagick module before issuing the display command. So I think that concludes today's walkthrough of the Land DA system. Thank you all for watching.